Hey everyone, welcome back to my channel. If you are new here, I am Akshay, and today we are diving into the exciting world of document AI. Specifically, we are going to learn how to fine tune the layout LMB3 model using custom dataset. Let's get started. Document understanding is crucial task in AI. Many companies like L&T, Bank of America, EXS service, they are into this process of extracting the information from given images. So it can be any document, PDF or receipt or forms. This is very crucial steps actually. So layout LM B3 comes with the state of art model from Microsoft side, and so it adds the visual information, making it perfect for extracting information from complex documents. So today I will guide you through the process of fine tuning a layout LMB3 on your own dataset. We'll cover everything from data preparation to model training and evaluation. So let's set up the environment first. We'll install some packages. These libraries are essential to layout LMB3 model, handling datasets and evaluation matrix. So SQL seek eval is for evaluation process. Transformer, as we know, is for creating the model. For our in our case, it's a fine tuning. Then we have the datasets library to import in any public dataset available from Hugging Face Hub repo. So let's first try to understand the architecture of layout LMB3. So what are the essential steps? We do the text embeddings. So standard token embeddings obtained from the input text. So first try to understand. Let's try to understand what layout LM exactly does. So we have given some images where we have some information. Like here we have, you can see we have the phone extension, date, name and phone extension, date, manager. So these crucial informations we want to extract from this particular image. In that case, what we do, we just create a bounding box of given particular text. Like here, let's suppose we select this as a bounding box, this particular information. Then we'll tag as a phone number or name. So again, it's a token we have to identify during the runtime. We have given any document and we have to extract out the names of the given document. In that case, it will be come out if we like creating a model using layout LMB3. Then for the date, for the manager, we need to do the same thing. So there are two steps basically: the training, where we first create the data or prepare the data. We have a tool called Level Studio, where we can basically create a bounding box of given particular text chunks and tag a label out of that. So that is the part of where we do the training. But in our case, we have already prepared the data. This data is this FunST layout LMB3. We'll use this data set and perform our training operation. So this is the problem. So in a broader level, we call it token classification for the given images. Images can be in PDF as well. Like we can convert those PDFs into images and then perform our layout LMB3 operation on top of that. So what was present in layout, the initial version layout LM. So layout LM extends the traditional transform based architecture by integrating layout information into the input and embedding. The key components are of layout LMR, text embeddings, layout embeddings. Now after that, what was done on layout LM B2 and subsequently in B3 is was visual embeddings, which was not present initially. So feature extracted from the image of the document, input representation. So basically, we also take the image as well in form of inputs. That is visual embeddings we have to perform. Then again, the tokens will be there. The bounding boxes information will be there. Uh, position embeddings, layout embeddings, 2D positional embeddings. These are the steps we need to have in our layout LM B2, B3. So we are talking about B3. Then we have the transformer encoder. The embedding are fed into the multi-layer transformer encoder, similar to BERT. The self-attention mechanism allows the model to capture the relationship between the tokens, considering both textual and spatial information. That is the important term here. So it also understands the visual or pixel representation of those images as well. That is the unique thing in this layout LM. Okay, so let's next we need a dataset layout. LMB3 expects a data in a specific format. So we'll use this from the datasets, import load datasets. Load dataset, we provide the this particular hub name, this particular repo name, that is this one. We copy it and we paste it here as an argument. Now we'll import it in the dataset variable. So what are the things present in this particular dataset? Let's try to understand first. We have the images. Okay, so the document images you will be processing, that is the thing. Then we have the tokens which are tagged over there. Let me open this one. Okay, so here we can see there are some levels. So zero is, I guess, the represents something. We'll see what zero means, but here the R&D term from this document, this is the R&D term, is tagged as a zero level. Then this column is level as a three, this one. So we can tag particular levels, and there is some coordinates available, like these are the uh, like left coordinates. So the top lefts are these one, these are the bottom right ones. For each bonding box, for each token bonding box, this is there, and the tag which we define for each token. So these three major information and along with images are present here. The levels can be like zero. These are the numbers for some text representation. I mean, it can be address, it can be name, it can be geographical location. We'll see what those represents. Okay. So we see the data set here. We have train, test, two particular data type of data set are available. Total number of samples present for the train is 149, and for the test data set 50. Total number of samples are present. So let's dive into the code. How does it work? So let's see some of the data samples here. So I am just starting the first index of this train data set. This is I assigning in sample variable, and then if I see the keys of that, it is ID, tokens, bbox, ner, tags, images, right? If we see the sample, the image of that particular key, we can see that images which are belong to the first sample. So this is the one. Okay. Now for that sample, if you want to see the tokens, we can just simply get the tokens, bonding boxes, which are the coordinates, and then NER tags, which are basically the numbers assigned to each token, right? Now we'll already be prepared the data set. This needs to be go over. Then we'll try to will import the base base model, which is provided by the Microsoft. This layout LMB3 base. Here we can see this one. We can read about it here. But in broader level, we already saw that these has essential things like visual representation in form of embeddings. That is a unique thing in layout LMB3 models. So this particular base model will use, and we'll try to fine tune our custom dataset on top of this particular model, right? That is called the fine tuning. So we import the auto processor, and auto processor has a from pre-trained method, and we just pass the uh, our model base name. Will make it as apply OCR as false, because we don't want to use this particular model for our inference purpose. We just want to fine tune this. So you need to pass this apply OCR as a false, not true. By default is true, so you need to make it false, right? Now here we just imported this in processor variable. Next we will see uh, what are the feature names. I mean, what are the total number of NER tags we have. I was talking about this one, right? You know the numbers 0, 1, 2, 3, something like that, but we don't know the name of those. So here we can see. Uh, Let me run this a different shell where let's see the data set. Data set we already see that this is divided into two parts: train and test. Let's go inside train. You will have the class called features or data set, and then we have the features class. So from the data set is a basically kind of dictionary. From this dictionary, we want this data set is a class. Sorry, from this data set class, we want this features. So I will type the feature attribute, not in like this format, in dictionary format. It is not need to be in this format. It's just an attribute. So you need to pass in dot. So you will get all the features of that trained data set. So these are the ID token, B boxes, and your tags images. Now we'll see the particular tokens. Sorry, not tokens. You need to see what are inside this on any tag, right? The classification class levels. Yeah. So here you can see that this one is a class level class, and there is a names available here. These are indexes represent 0, 1, 2, 3, 4, 5, 6. So the numbers you were looking are these has the meaning of this particular text, right? So once you recognize, so think on that. Once you have the model in place, you in the runtime you will provide a unique image or different image. Then what it will give? It will give you those NER tax number, not the NER names. But as a consumer or the client, you need those tags. What does it means? It's a header, it's a beginning header, intermediate header, beginning question, intermediate questions, those things, right? So you need to convert back those numbers, those 0, 3, 0, 1, 2, 3, 5, 4 back to these strings, and vice versa. You also need. So you will create two dictionaries. First is ID to level, and the second is level to ID, right? So if you go into the features and you go into this NER tags, this is dictionary, so you can use this notation NER tag. And NER tag you have this class level. This is inside again feature, so you just type this feature as an attribute, and then from this feature you will get these names, right? So again it's a names attribute, so you type names. Now you will get a list of these tokens name, those NER names, not tokens name, sorry. So once you get this list, you can have this particular index. So I assigned in the level list this particular list. Here you can see. Then I create the first dictionary called ID to level, where I iterate through these list of NER tags and get the index number of that and then corresponding value. Then here I just reverse it, value and then index number. So let's run this particular shell, and you can see. So you also need the how many levels we have, right? You also assign this make a length function of the level list. Now you can see those three values. So you can see ID to level, index to level. These are the indexes, and these are the particular level names of NER. Here the vice versa, and this total number of length is 7, right? 0 to 6. So number of levels are 7. Now let's move further. I just assign some names, the constant names in some variables, so that I don't need to do any kind of mistakes while typing these particular strings, right? or just assigning these variables. You will see later the use of this. Okay. Now we'll prepare the data set. So I created a method called prepare examples. I will pass the data sets each sample out of on this, or in one shot I will provide in a batch instead of one sample at a time, because if you provide one sample at a time, then you are not utilizing the batch processing or vectorization. So for the examples, to get the images, this image column name, that is image, this is images. So from why images, because it's examples is a batch number of samples. Then we have this text column name, which is words. Here we call it tokens. This is tokens. Then we have b boxes, then word levels. Now we'll pass these images to the processor as well. Words, boxes, word levels, truncation needs to be true. So so the length of the token length is supported by the encoder part is 512. So 512 is the maximum number of tokens it consumes, right? That is the limitation. So this particular document needs to be have less than 512 tokens. For more number of documents you want to process, then you can create a different batch, right? Let's suppose the length of this is higher. There is a second page where you have, let's suppose you are processing the PDF, and PDF can have multiple pages, right? So for each page you can have one samples. Make it as a one example. The second page as a different example. Like that you can make it, right? To overcome this situation of 512 tokens. Not this return the encoding of that processor. Processor is just the initialization you have done for this base model, right? After that you just create the features. So features have things like pixel values, input IDs, attention mask, bbox levels. These are just like kind of class we have, right? So the pixel value is a three-dimensional array, which is a kind of size of 224 pixels of each side of images. It's a RGB image, so red, green, black, everything has needs to be have total number of 225, 224 tokens, the pixel values. Then you have the features, which is a int64, attention mask int64. It should be sequence. Then the two dimensions will be bounding box, because the coordinates will be represented as in two dimension array. You can see here. So it's a two-dimensional array, right? Inside that we have each list, so it's a 2D. Again we have this sequence levels, it's in 64. Why in 64? Because you will provide the index of that, not the string itself, right? This is the features class we have. Next, what we will do, I will selecting 60 training examples and 40 validation example or test examples. So you can see here we have already the data set trend sample is there, right? That is the beauty of this one data sets. You just provide a map function out of this train sample, and in the map function you will provide the function you prepared here, right? So what it does is just create the embeddings out of images, words, b boxes, bounding boxes, and word levels. You will provide a key called batch equals to true, so it will send those samples in batches instead of single sample at a time. Then you want to remove some columns, so I don't think so id is required. So id is not required. Even the lot of all the train column names, for example, if go into the training train data part, I see. So ID tokens, B boxes, near text images, everything is not required, because I already process through base model, right? Processor is the class which I use, and everything I pass over there. Now encoding is enough for me for the X part. The Y part is just a corresponding tokens of each one. It's just token classification for any other problem, right? So I remove all of those columns. Here the column names are basically the train features, which I not required after that, right? Then features is just a the class I created so that it will format in this for it knows that we need to format in this way. Then this train dataset is prepared. Let me run this. It's 60 examples of each training example and the 40 is test one. Okay. Now let's see the train dataset. You can see the new features are right now these pixel values, input IDs, attention mask, box levels, which we here see in the features class, and here we also make made in this way format as well, right? Providing these things in processor object for the this is for the keys. Okay, we can see the sample image. So this is the first image we have to process. Right, sample image of train dataset. Now we can just extract out the example variable of first train dataset and see what are the input IDs. So these are the input IDs we have. You can see some of the dataset like as some of the keywords are added by the model itself. So you can see the pad token is added in the last because it not reaches to the 512. That's why and the padding they added this by default as added. So it's a tokenizer input IDs, right? You can see the other things as well. What we had input IDs, attention mask, box levels, right? Let's see the pixel values. What is in the pixel values? Yes. Where are these ones? Okay. So argument IDs list object cannot be interpreted as an integer. Hmm. Yeah. So the thing is, this decode function is expecting to have the input IDs. So that's why you can able to map back to the string. But these pixel values are just a number between 0 to 1. So if it is 0, then that is kind of white color. If it is 1, then it is kind of having some information, right? So you don't need to convert back to a string, right? It's not possible, right? So these are the pixel values. Now we'll convert the train data set into the torch notation. Ultimately, these needs to be converted into torch tensors. So there is a method called set format. You just apply that in the train data set, and the train data set is now in the format of torch tensor. Torch is a library created by Facebook. So now this one example, if you want to see what are the shape and sizes of those input IDs, pixel values, boxes, labels, we can print those shapes and the data type as well. Now you can see there's a torch data type. It's a three-dimensional array. This is a two-dimensional array of this bonding boxes. So four coordinates of each token, right? And the size of them are 512. So this is the torch data set now. So there is a catch actually. If you want to use this load metric from the given data sets, you will end up on failing audit, right? You will not find the solution of this mostly in the blocks, but Let me give you the solution of this. If you see the version of data set, just want to run the pip freeze, just grep it data sets. You can see the version. Yeah, the version is 3.0.1, right? It is not working to load this seek eval. So you need to downgrade into the 2.21.04. You need to install it. Now you can see it's downgraded to 2.21.0. If you run this cell again, you will be able to load it. This particular metric. This is the particular metric which you want to use for evaluation purpose. Okay, now we'll create a method for the computing the matrices. So this matrix is kind of different matrix for this token classification. So you can go through this particular method. It basically create the precision, recall F1, and accuracy for us. We already aware of this precision, recall F1, and accuracy. So this method will be helpful on that part. Now we'll create a model for this token classification. So in coder part, we use this particular base layout based model, which is helpful for encoding this. Now we'll prepare those things already for our input, that is b box, pixel values, images, those coordinates. So coordinates or b box both are similar. So we again load this base model for different purpose, that is for the token classification, because every input feature is right now prepared. So we load this model again, but we'll use this class called layout lmb3 for token classification. Initially it was auto processor from the transformer, as you able to recall. So this is auto processor from the transformer. Now it is a layout lmb3 for token classification from transformer, right? So you will provide those particular things which are required to inference back, that is id to label dictionary, label to id dictionary, which we already prepared, right? We initialize this model. Now we come to the main part where we, so there are a lot of ways to train a model. First is obviously is to write all those gradient descents and the backprop algorithms the way it, we need to calculate the gradients, and then for like backward prop, and then recalculate the loss function, and then again we need to update the weight. So those are the manual way, but the Hugging Face provides this trainer class from the transformer library of the Hugging Face transformers, and there is a class called trainer. So trainer class is helpful to train this any model. I will be using the trainer class. So in the trainer class, we can initialize some of the training arguments first. So this is the output directory where all the logs will be created, the artifacts and those things will be created on this particular folder. Then we have the max steps, which are the total number of epochs we have. We can uh, override the max number, the n epochs of from this max step argument. What is the train size batch we want to prefer? I would recommend like 4. This is for the test purpose, so I made it 4. But always use 2 raised to the power n thing in the batch process. 4, 8, 16. Because if you see the CPU architecture or GPU architecture, it has mostly 4 cores, quad cores, 2 cores, 4 cores, 8 cores. Even quad core is also there. But this is a good way, like putting 2 raised to the power n thing. So each CPU take one sample each time, right? This is learning rate. How we want to receive like reduce the gradient. So that is 10 raised to the power minus 5. Evaluation strategy. So in each steps I want to perform the evaluation strategy. The evaluation step is 250, and the load data set model at the end true. Load based model at the end true. Like let's suppose 1000 epochs max steps ran, but in 600 epochs max step you found your best model. So at that point it loads that point model even, not in the 1000 iteration one. So matrix for best model is the we are picking up based on the accuracy. Okay, let me initialize these training arguments. Now here comes the main part where we have the trainer class. We provide the model, which is the layout LMB3 for technical classification from the Microsoft layout LMB3 base. Then training arguments. These are the arguments we initialize it from the training arguments class itself. We provide the train dataset, eval dataset, which is test dataset. Then the processor you need to have the tokenizer, then the data collector, then compute matrix, which we use the seek eval for that, and we create a method, right? uh, Once we run this, we have created this trainer object. Now we can start by using the train method. So once we click on this train, we execute this cell, we see the training has started. You can see the consumption of GPU. So now it's reached to 7.4 GB. RAM is not increasing because I'm running in on top of GPU. Otherwise, it'll be very slow. Let me pause the video and we'll come back once the model is trained. Okay, finally the model has been trained. So you can see the loss has been constantly decreasing initially, but I guess it requires more number of epochs. I ran for 1000 steps only, got the validation loss of 1.97. Precision is okay, 86%. Recall is 90%. So recall needs to be good because it needs to be correct on the original document, the actual documents. The F1 score is decent, 88%, 74% is accuracy. So number of true positive plus true negative divided by total number of samples or total number of samples examples we ran. So that is the accuracy. It's a decent enough, but I would recommend go for higher number of steps. You will get a good, you will end up a good number of good accuracy. Let's see the folder which we created during the training, that is called layout LMB3 fine tune CORD 100. So you get those folders over there, checkpoint folders. These are the artifacts, the basic things about the models. Now we reach to the point where we can save our model. So model.save pretend method will be helpful on this. I name it layout LMB3 fine tune custom, and the processor also needs to be saved for further use. During the inference, these are the weights we need to carry on, right? So we execute this cell, and now it is saved in the given name. Let's refresh. So this is the processor information. This is model information, the fine-tuned model information. Now we load the model. So this process will be followed during the inference. Once the fine-tuning has been done, we can load this fine-tuned custom version, and also we can refer the processor this base version as well, because nothing has been done on this processor part. Only the model part we fine-tune, right? This encoder part will be remain same, right? So we are taking one example of test data set. Zero is the indexing, and the one sample I took provided to the processor object, and I pop all those levels because in the test data set we should not have any kind of levels, right? So now it will return something, those logits. So this total number of 512 tokens. This is one dimension vector, and this total number of NER examples, NER samples, NER tokens were seven, right? So seven are total number of different tokens, different NER tags are there. Now, if let's suppose we want to visualize this for this given this data set. So this is the method I prepared for that, where I just draw those tokens of given image. Yeah, here we can see. So this is the question, this is the answer, this is other part where there's nothing level and value. This again note is the question, this is the answer, right? Question and answer. So in the given format, we are basically perform the labeling. These are the others again, right? Performed really well actually. This is other. This is the question answer. Question answer. This is again an answer. This is header, right? Okay, that's it from my side actually, and thank you for watching this video.